Our previous topic was work, and we said that work was force times displacement, but also that it represented a change in energy. And the first type of energy that we're going to talk about today is kinetic energy, or the energy of motion. Now, the formula that we have for kinetic energy is E sub k. This is the version of notation that we're going to use. We're going to talk about several different types of energy, and it's easier just to change the subscript, K, P, S, than it is to change to an entirely new variable. So E sub k is equal to half mv squared, half mass times velocity squared. Maybe you'll notice that that's pretty close to the momentum formula. Momentum is determined by mass and velocity, so is kinetic energy. It is a little bit different, and we're going to show where that came from in a minute. But first, we said that work was a change in energy. And so when we look at work as a change in energy, work equals change in EK, then we can say that work is final minus initial kinetic energy. Okay, and so when we're doing change in anything, it's final minus initial. So the way that we've been writing that is like this: EK2 minus EK1, but there are some places that you're going to find the notation 0 and 1 instead of 1 and 2, or EK0 and EK. It's okay. We're going to use this one, and it'll be fine. So if we start here, we're going to find where our formula for kinetic energy came from. Now I'm going to try and fit the derivation in over here. We'll see how squished we get. Okay, so we're starting with change in EK is equal to work, right? And we know that work is also force times displacement. Okay, we're going to do a little bit of subbing in other formulas to show where the kinetic energy formula came from. So bear with me here. You're not supposed to know, hey, how should I have known how to do that? It's okay. We're just deriving this formula. So force is mass times acceleration. And so now we have mass times acceleration times displacement. And now comes a little bit of a tricky part. This A change in D part, we're going to sub that out with a kinematics formula. So the kinematics formula I'm talking about is V2 squared equals V1 squared plus 2AD. Okay, and notice this AD part over here. Okay, we're going to rearrange the formula to get AD by itself, and then we're going to sub in that extra bit back into our original formula. Okay, and so what we end up with is A change in D, or A acceleration times displacement, is equal to V2 minus V1, both of those squared, divided by 2. Okay, now we're going to take this piece of formula and sub it back into this MAD thing. So then what we get is, just a second here, what we get is mass times V2 squared minus V1 squared divided by 2. I just divided the whole thing by 2. It doesn't really matter where the divided by 2 goes. Okay, and so if then we distribute this m into the brackets, we get half times mv2 squared minus half times mv1 squared. Okay, so we end up with half times mv2 squared minus half times mv1 squared. Okay, Now, what we're saying is that this is change in energy, right? Work is change in energy. And so change is final minus initial. So that would make this piece over here EK final. And it would make this piece EK initial. And we can assume that our initial energy is going to be 0. And so then our formula for any kinetic energy is half mv squared. Okay? So our formula for kinetic energy is half mv squared, and that came from our formula for work. Now, it's important to note that in this formula, right down here, it is assumed that the height of the object does not change. Okay, so you can't really separate all the different kinds of energy and work with them individually in most circumstances. Often, if something's kinetic energy is changing, maybe its height is changing as well. If you throw something into the air, you are adding kinetic energy to something, but you're also adding gravitational potential energy to it by changing its height. But we are going to focus on just the parts of change in energy that deal with change in motion without a change in height. Okay, so bear with me. We're going to put it all together in a little bit, but for now we're just looking at changes in motion that do not include a change in height. So we see that something's kinetic energy depends on its mass and its velocity. Greater mass, greater velocity means greater kinetic energy. Lower mass, lower velocity means less kinetic energy. I want to give you a couple examples of that from my own house. You may not know this about me, but I was once a semi-professional golfer. See? The ball has a very low mass, but I'm exerting such an enormous force on it that it attains a very high velocity. See? Can hardly see the ball. Which leads to a very high kinetic energy. And now an example of low kinetic energy. Can you kick it? I'm telling you, he can kick better than that, but off day. We're going to finish this topic off with a little bit of hopefully simple problem solving. So a 100 kilogram man is in a car traveling 20 meters per second. Find the kinetic energy of the man. So kinetic energy is half mv squared. If you know mass and velocity, you can figure out kinetic energy. So kinetic energy, EK, is half times the mass times the velocity squared. So the mass is 100 kilograms. And the velocity is 20 meters per second. We're going to square that. So half times 100 times 20 squared is equal to 20,000 joules. Okay, our units for energy are the same as our units for work, joules. Okay, so hopefully that one was straightforward, not a big deal. The car strikes a wall and comes to a complete stop after the car collapsed 1 meter. So cars have crumple zones in order to protect us a little bit, to decrease the impulse acting on us, and hopefully preserve our organs. It collapsed 1 meter. Find the force exerted by the seatbelt the man is wearing. Okay, so we're looking for force. We are given the displacement, and we already know the starting kinetic energy. Okay, and if it comes to a complete stop, the kinetic energy at the end is going to be nothing. So we now know the change in kinetic energy. Okay, and we know that work is change in kinetic energy. In the case where height isn't changing, which is what we're going with right now. So work is force times displacement. And that equals EK2 minus EK1. That's the change in kinetic energy. We know that the displacement is 1 meter. Okay, so we're going to find force equals kinetic energy 2 minus kinetic energy 1 divided by 1 meter. Okay, so kinetic energy 2 is 0 joules minus 20,000 joules divided by 1 meter. And that gives us a force of negative 20,000 newtons. 20,000 newtons backward, right? So the man was moving forward in order to arrest that kinetic energy, then force had to be applied backwards. And so we get a negative force, or a force backwards. Okay, so our force is negative 20,000 newtons. Let's put a vector on that. The force applied by the seatbelt is 20,000 newtons backwards. Backwards. There you go. Okay, one more example. A baseball is thrown and the velocity diminishes from 20 meters per second to 15 meters per second. If the mass of the ball is 0.15 kilograms, how much energy is lost? This is asking us for change in energy again, right? So it's asking us to calculate work. We're looking for work. We know that work is change in energy. So it's EK2 minus EK1. Now in this case, neither of those is 0. The velocity diminished from 20 meters per second to 15 meters per second. So we had kinetic energy at the beginning and we had kinetic energy at the end. So then we're just going to put both formulas in here. So work is equal to half times the mass of the baseball, 0.15 kilograms, times, this is the velocity at the end, so it diminished to 15 meters per second. So the second one is 15. Minus half times 0.15 kilograms times 20 meters per second squared. Okay, now you probably can notice that you have common factors over here. So you could have just done half times 0.15 times, in brackets, v2 squared minus v1 squared. That works totally fine as well. And in most situations, the mass of the object is not going to be changing. So then doing it like that will work totally fine. Okay, so our work done here is going to be negative 13 joules. So that says that 13 joules of kinetic energy was lost by this baseball as it was flying through the air. I guess from air resistance. The loss is 13 joules.